welcome everyone. Welcome everyone to part two of our Solar 101 class that we're going to do. Today we're gonna start off with some basics, some very basic stuff before we actually get into some of the meat of it, because there are some people out there that just don't necessarily have a grasp on some certain things. So welcome. I'm glad y'all are here. We got a lot of fun things that we're going to do in the videos to come. But again, I'm going to approach a few things as if you don't know anything. So if you already know some of it, just bear with me, because I'm going to try and help build a foundation for, like I said, for the person who may not have any knowledge around it, and we want to give you enough knowledge that you can be successful in putting together some components and that you purchase in order to have a system. Alright, so for very first thing that I want to talk about is what kinds of systems that we're talking about, and I want to make it very clear in the beginning here that I, for personal reasons, do not advocate doing grid tie anymore. And because you may be doing the system on your own, the issues that you may end up with trying to tie your system to the grid may be so immense that cost-wise or issue-wise, it may be a tough hurdle for you to overcome. The regulations that are out there as to what you can and can't do, whether they'll buy back extra or won't buy back extra in your particular power grid and company that you are with, and then the regulations is who can do what, whether you can do it. There's a whole list of hurdles that could very much stop you in your tracks mentally, not necessarily physically, but mentally, in wanting to proceed in gaining some solar independence, some power generation of your own. So I do. And I started doing this back in 2013. Only after 2 years of working my solar company, I stopped doing grid tie. I did a bunch of them, and I've learned a lot. And we may discuss a little bit of it as we go along if I feel like I want to add something into the conversation. But for all intents and purposes, we're going to discuss only off-grid systems, because unless you have the financing to overcome all the potential hurdles from your state authorities, from your electrical regulations and all of that, and you decide you still want to do a grid tie system, the only grid tie system that I would even remotely advocate is a grid tie battery backup, because straight up grid tie systems will and are intended to and are designed to shut down in a grid down situation, which leaves you SOL up the creek without a paddle. And we discussed this when the fires were raging through California, and why all these people who had these wonderful solar systems and solar panels all over the roofs of their homes didn't have power when they did their blackouts and their power shutdowns. So this is specifically only for off-grid systems. All right. The first thing I want to jump into is some basic concepts and understandings, and I'm going to try and keep it short and simple. We're not going to get extremely deep into this, because I don't think it's necessary, other than for you to have a basic knowledge. Most people are concerned with, or aware of, and familiar with AC electricity, and we won't really get into a whole lot of that, because that's That's the service end of the inverter, and pretty much everybody knows how to plug in, okay? Everybody knows how to plug in. We will only talk about connecting into a wired house in some form or fashion so that you can use your current wiring distribution in your home like you would normally. How do you make it work in your house? We will only discuss that end of it towards the very end of all our classes. But most people are aware of AC. And AC is, you basically you have what's known as a hot, a neutral, and a ground. And in the hot and the neutral, many times those are interchangeable because what is electricity? Electricity are electrons that are in motion, that are moving, and they're moving across a conductor, and that conductor is a pathway for the electrons to move to create motive force, to make things happen, to either be converted into heat via incandescent kind of light or go through a motor. Mostly motors. You know, the compressor in your freezer is a motor, and it compresses air, but you're turning a motor. Motors in an air conditioning unit for the fans, and then also for things like computing power and stuff like that. You need those electrons to move, and then you need a conductor for that. Now, first off, all conductors that we're going to talk about are also resistors, which means although electrons can flow across them very well in some cases, and some are better than others, copper's the biggest, most commonly used conductor, but silver, there we go down that subject, is the best that we know, other than very difficult superconductors that are not capable of normal usage because of the conditions that are required to have superconductors actually function as superconductors. So we use conductors that have resistance to them, and we need to understand that. The concept is this: in electricity flowing on wires or copper wires, that we got to understand how it works, how much you need, and that kind of thing. So that's today's discussion. A little bit of math we're going to get into also, but the big difference is AC works differently because electrons flow both ways on the same conductor. So even if it's a hot leg, electricity flows both ways, and the neutral leg, the electricity flows both ways. So if you have a circuit where you have a loop, it's flowing back and forth on that. In a solar system, everything is either positive or negative. In other words, there is a direction of flow within your circuitry, and you have to stay very aware of that direction. You need to keep your positives and negatives correct and clear in your heads, because a lot of normal electricians have tried to do DC systems, and they don't realize that you just can't cross connect things, because what you end up with is short circuiting things in ways that you don't want to do. When it comes to wiring your solar panels and wiring your battery systems, it is going to be critical that you are very aware of your wiring patterns and the way those patterns have to be connected. There are very direct circuits that have to be created in doing so, and we're going to get into all of that. Let's see here. I don't know if I paused it or not. Okay, still trying to learn this new system here, so bear with me. I'm trying to use some new features in this recording software. Alright, then the next thought we want to step into is a basic math formula. That's a real simple one, but I've got to explain to you what variables are, what certain variables are. And if you want to, you can take notes. Be a wise thing to do. But generally, I'm not going to do like chalkboard stuff yet. I'm going to give you a homework assignment at the end of this so that you can kind of study things and kind of get a feel for and start to learn and see what we're going to need as we go through our systems designs towards the very end of things. So in this math problem, I want to give you the basic simple stuff that you need to know in order to put a system together. Because we're going to talk about components, we're going to talk about panels, charge controllers, inverters, and batteries and all that. And you're going to have to understand how to connect them and with what to connect them, what kind of conductors that you're going to need, what kind of wiring. And we're going to get into wiring sizes, because the size of your system may require different size cables, and because each and every one of you are going to do different size systems and stuff, you're going to need to know that what you're putting on your batteries and your solar panels and connecting everything, that you're using the proper wiring. Now there's some generalities, I will share those at the end, but I want you to understand and know the hows and whys first. So the math problem is this: voltage times ampage equals wattage. V times A equals W. Now, let's talk about this. The easiest way for me to explain the electricity, the voltage, ampage, and wattage, is to do it from the garden hose analogy. All right, so instead of using a copper wire conductor, I want you to visualize that copper wire conductor is a garden hose, okay? And that you make different sizes of garden hoses for different purposes in the amounts of watering that you have. And in some cases you have you got little garden hoses for watering your garden, and then you got big hoses such as fire hoses for putting out fires that need huge amounts of volume. So in that formula, voltage times ampage equals wattage, let's look at the first variable, voltage. What is voltage? Voltage, in the analogy of the garden hose, is your pressure. Do you open the valve up and it just starts to slowly come out? Or do you crank the valve all the way open and it really wants to come out because there's a lot of pressure behind it? So the higher the number, the higher the pressure. So 120 volts is a pretty high pressure, and that's enough to hurt you, kill you. If it goes through you the right way, it could stop your heart, and it could be very dangerous. Low voltage is not as likely to hurt you. You can pick up a 1.5 volt battery and you can touch either end of it, and the current or the amount of energy that's flowing through it is not enough to do you any harm. The 12 volt batteries, or 6 volt batteries that we'll use in our systems, they're a lower voltage, but because of the ampage, there is almost enough, quite a bit enough power to actually hurt you if it goes through your body just right. So you gotta be careful, no matter what you have, and in the way of voltage, understanding the W side of it. And what is W? W is the watts. But before we can get to the W, to know whether it's, how much we've got, which gives you a clue to the danger side of things as well, we also got to know what the A is. And the A is referred to amps, voltage times amps. And what is amps? So if you compare that to the garden hose analogy, amps would be the volume of water going through the hose. So let's look at this. Voltage times amps is pressure times volume to get your quantity, watts. And watts is basically how much. How much in a given period of time do you accumulate in your equation? So my solar panels, they got 3 numbers on them. All solar panels will have these 3 numbers, and their voltage and ampage, how many volts, how many amps, and for a total of the watts. So your solar panels, you're gonna have a watt rating. How many watts are those? Are out there at 260, 270 watts, but they're like 18, 19, or excuse me, these particular panels are around 33, 36 volts. I don't remember the exact voltage on them. And then the ampage is around 9 or 10 amps. So that gives me a total of 260, 270 watts. All right. So what we're looking at is when we take a look at the electricity, and we want to start doing this math problem, we need to know what the voltage is, and we need to know what ampage is to come up with the watts. So how fast is that water, or how much pressure is on that water, will make it move quicker. The quicker the water moves, the more amps you have, or more amps you can have. Doesn't mean you have to have that many. You can do 110 volts and only do a milliamp. It's not going to have as much wattage. It is the wattage that is the dangerous part of this equation when it comes to possibly hurting you or getting shocked from it, or the current going through you and or part of your body, or for the motive force that you're going to get in being able to run things. Because in the end, you're going to need to know how many watts you have, and watts is on a time basis. So like my freezer runs off about 80 watts. Okay, that's good to know. 80 watts. That means if I want a system to run my freezer, I need to have a system that in the end of the equation, I'm getting a minimum of 80 watts in order to run that appliance. So you can tweak this equation with your garden hose so that you can get a lot of wattage through any size garden hose or any size conductor. The problem is because electricity is not only is electricity energy from an electrical standpoint, but because you're I know I'm kind of working into this in maybe not the best way to say this, but because that is a resistor, your copper line is a resistor, it can only handle so much before it starts converting that electricity into heat, because there's only so much that goes through it. Does that make sense? I hope you get that. So I can take a number 12 wire and I can put 800 watts through it, but because there's so much volume, so much pressure going through at once, it will resist that at a certain point, get hot, and virtually melt the insulation off of it, because there's way too much. I know this is hopefully this is simple enough for you. So the concept is this: as we are going through and we're determining the voltages and the ampage to come up with a wattage. At different stages in our system, we're going to have to size our garden hoses, our wires. Okay? Does that make it simple? The whole understanding is we need to, one, we're gonna need to match our system's components based on voltages, based on ampages, and to come up with the wattages. But we're gonna have to connect everything with the appropriate size garden hose or the appropriate size wire in order to make sure that we're running safe, running cool, and we're getting the most efficiency for our system. Because the entire system, though it is a conductor of all your power, so once and we'll get into the solar cells later and what's going on with the solar panel, but once you get your production, which is your solar panel, to move those electrons via the sun hitting them, we need to carry those electrons all the way to your freezer in the most conducive way. We need the right size equipment, the right size wires, the right size everything all along the way in the way we handle getting that sunlight to make your food cold. So the math is really simple. Your wattage, or the amount of electrons that are moving in a given period of time, are a function of two variables: how much pressure or voltage you're putting into a conductor or your garden hose, and how much volume. Because you all know this, when you take a garden hose and you put your thumb over the end of that garden hose, what happens is the pressure starts to build, and then it starts to squirt out at a much higher pressure. And what happens, in order for what the system wants, which is, the system is, if you're talking about like a city water system, in order for the wattage that is being pushed into that via voltage and the volume ampage to go through that garden hose, in order for it to continue going at the same rate, so the wattage wants to stay the same, what happens is something changes in the garden hose, and the garden hose and the pressure builds, which means the voltage will go up. Hypothetically speaking, it goes up in pressure in order to get out the smaller constriction. So whenever we put the system together, we're going to want to make sure that there are no constrictions, and that our plumbing, our electrical plumbing, is adequate throughout the entire system. I know that's a kind of an awkward way of doing it, but it has been the easiest way for me to correlate somebody who does not understand electricity to picturing it in their head. The garden hose analogy always seems to kind of work. So we're going to learn voltages and ampages and wattages on all our different system components all the way through our system. Because when we get to combining certain parts of our system, like combining solar panels or combining batteries, we need to know which one of these variables changes. In brief, if I'm putting 3 strings in, I'm wiring 3 strings together. So this panel says 33 volts, this panel says 33 volts, or 33 volts 10 amps, 33 volts 10 amps, 33 volts 10 amps. What do I have coming out of it? You need to know how to do that math. You need to know how to add up your panels, or how to add up your batteries. If you're going to do, if you got like what I've got under my feet right here is a 6 volt a 6 volt deep cycle golf cart battery. If I put 2 of them in a row, um, what is my voltage? What is my ampage? You need to know these things because you're going to have to do the math when you're putting your components together. And then you're going to have to wire size these components based on the system that you put together and how big that voltage is, how many amps you're going to pull from it or push through it based on the conductor. And then you want to make sure that you don't have anything resisting at any point, and that it's capable of conducting or having the electricity flow in such a way that things stay reasonably cool. Now, not always going to. I mean, there's days that I've used my batteries when I've got full sun and I'm trying to charge my batteries back up, that some of my wires will get a little warm because they're a resistor and there's a whole lot going through and there's resistance happening. But the idea is we want to keep that to a minimum because we want to, keep possible issues, to fire issues, shorting issues, and that kind of thing. So understanding the voltage, ampage, and wattage equation is something you need to have your head pretty much wrapped around the basic aspects of it. So that's the simple thing. That's the easiest thing for you to start with as we get started in our discussions. Now, I do have something I want to share with you because this is going to be your homework assignment. Switch. There we go. Minimize this. And all right, so quick homework assignment. If you haven't already seen my battery cabling systems, there's 2 videos here. This is a video I've already done that talks about it, and you can go back and rewatch those videos. Those are ones that I've already made available for a specific system. Now, we're talking about designing any system, so what aspects I talk about in this particular system, and I've got a diagram of how that kind of works on this particular, this is a full house system. This is a 220 3 kW system off-grid that is capable of, when I got it installed, that is capable of feeding into the main house system and running their well pump and stuff. But for the sake of today's first step, we want to look at I did a let's see, you can do this. You go to Google and just type in wire sizing chart. Okay, and then that took me to a website, so I pulled up the full chart. Okay, this is going to be your homework assignment because you're going to need to know, based on, and now this is a standard and metric, based on your ampage, based on your wire size and distance. So you start with 16 og, 14, 12, 10, 8, 6, 4, 2, 1, 0, 2, 10, 3, 10 og, 4, 10 og, which is 4 og, 2 og, 1. Then you got the 2 aught right here, 3 aught. So when you have, and I want you to pull one of these charts up and I want you to study it. I want you to see the correlation in your wire size, in your amount of distance to the amount of amps to get how you size these wires. Because you want to understand, let me go back here to there. You want to understand that depending upon how far you have to run, your panels from where your batteries and your charge controller are may determine how big your wire size is. For me, I'm pretty close. I've run on where I'm at. I've run as little as 10 og, but right now I think I've got number 8 og going from my panels to my charge controller, to make sure that I have enough of the a big enough garden hose to handle all the electrical water flowing through my pipe, if that makes sense. So the simple concept is this: the lower the pressure, the bigger around the pipe needs to carry a larger volume. So if you're going slowly with your pressure, your pipe needs to be bigger. That's why basically the battery cables, and here I'll pull one off of here right quick. Battery cables, oops, the battery cables are a much bigger, thicker wire than little ones. I don't know if I'm going to get that here. So that's a Cat 5 cable. It's going to the computer that's sitting on the bed that T's working on right now. And that Cat 5 cable carries a very low voltage. Very low voltage. And a very, very small amount of power. Only a part of an amp. Very low amount. So you only need a little wire, little garden hose, little amount of water. But because we're going to be dealing with larger volumes, you need to understand and learn how to size your wires. So that's your homework assignment. It's on you to learn it. I've given you the basics. You can go to other YouTube channels. Maybe find if what I said about the garden hose analogy isn't there for you. There are other guys out there that might explain it a little bit differently. But before we talk about components, and before we talk about matching components, and before we talk about combining components, like doing a string of batteries and stuff like that, you really want to kind of get your head around. DC is a straight path that you're going to have to wire in a circuit that you cannot cross things like you can kind of with AC. AC, you can flip those two conductors, and sorry, just want to see who was on the phone. And that get your head wrapped around voltage times ampage equals watts, because when we go to design a system, we're going to want to find out what our wattage is. We're going to design a system around what we need that system to do, or have available for us if we want to do. We need to know that. But to get to there, we need to know the delivery system, because the conductors and the wiring are going to be the delivery system. And if we mess up on that in any form or fashion by doing it too small, we will have issues. So I know this is isn't getting very deep, but having a knowledge around wire sizing is going to be very, very critical for all the things we do. Now, once we get to talking about it, I'm gonna make suggestions on wire sizing. But if you don't have your head wrapped around it, you're not going to be able to make sure everything's connected properly. So that's all I got for you for the first step. I know this is a small step, but it's probably one of the most important steps, believe it or not. As simple as it is. Y'all take care, and we'll be back with you soon. Take care.